I had one for you all to try, and then we'll go on to something different. Still about Turing machines, but a little different, change of pace a bit. But anyway, let's try a Turing machine for, this is a little warm-up. X in A, B star, such that the number of A's is equal to the number of B's. But they can be in any order, all right? So this is different from A to the n, B to the n, has all the A's at the beginning followed by all the B's, but this is just any old ordering. So it's something like, you know, A, B, A, B, B, that, right? Has 3 A's and 3 B's. All right, we are still going to do this by marking letters one at a time, only you can't depend on the ordering at all. So my basic strategy will be, I just start with whatever letter I start with. I see A here, I'm going to mark this A and then move to the right until I find a B to match it off with. Because I want the same number of A's and B's, I'm going to match up each A with a B. Only I have no idea where they're going to be, so you just have to look through the whole string. Seeing this A, I go across the whole string looking for a B. And then once I find it, I'll mark off the B, and then I'm just going to go all the way back to the beginning and then repeat the process again. That's my basic strategy here. I hope that made sense. So I'm going to start, this is just my starting state, and I'm immediately going to have 2 branching paths. One will say A bar R, and the other will say B bar R. So depending on if I saw A first, then I'm going to go looking for a B to match it with, versus if I saw a B first, then I'm going to go looking for an A to match it with. These will, so there's going to be sort of one track across the top and one track across the bottom, which will look essentially the same, but the roles of A's and B's will be reversed. All right. So I mark off this A. This is going to have a looped edge on it saying, move yourself to the right, past a bunch of stuff you don't care about until you find what you do care about. Anyone want to suggest, what should I put on the loop here? This would be, you should go past some things until you find what you're looking for. Is that, are you just? Yeah, so I don't care about A, right? Having marked the first A here, I am moving to the right. Really, we're looking for a B, which means if we see an A, we should go past it. Anything else we should go past? B bar, yeah, if we see a B that's already been marked, I should go past that. Anything else? And also A bar, right. If we see A bars or B bars, we should move past them. All right, great. If you see a B, you should mark it. And actually, I think this is sort of where the 2 paths come back together. So it's going to look like that. If you see a B, you should mark it, and then you can start moving to the left. And my intention is to go all the way back to the left, all the way to the beginning of the string. So I'm going to put a looped edge here, moving to the left no matter what we see until we see a blank. So I'm going to go A-L, A bar, L, B-B-L, my favorite, B bar, L. Would you believe it? When I first taught this class, I've been teaching this class for several years, there was no such thing as BBL. Nobody knew what that meant. I think the students learned what that meant before I did, but eventually I caught on. And now I mention it as often as possible. So in this state, we're going to move all the way to the left until eventually you see a blank. That means you sort of overshot the left end, and then I'll just go back to the right one position. Blank, blank, R. All right? And then, after seeing that blank, we will be pointed at the first letter of the string, which I suppose after you go through this once will be marked off. Now, actually, I don't want to mark that first one again. I want to sort of automatically move down to the next unmarked. And we can make that happen by just putting another loop right there. A bar, R, and a B bar, R. So this will, at the beginning of the loop every time, automatically will push us to the right until we see an unmarked letter. All right. I think this is basically it. Now we need to fill in the bottom, but the bottom track there will be the same as the top, only the roles of A's and B's are reversed. So the bottom, Sorry, it's kind of hard to see my thing on the top. Maybe I will put these guys over there. All right, the one on the bottom, I'm going to say, just like up there, only A's and B's being reversed. So we should this time go past B's, B, B, R, and then we also have B bar, yeah, sorry, B bar, R, and AAR. No, not AAR. That's what we're looking for at this point is A bar we should move past. And then here I go A bar, R, like so. L, I mean, not R. It probably doesn't matter, but it ought to be L. All right. This is the main body of the Turing machine. Any thoughts about that one? I hope that everybody feels okay about that. Now, how do we decide when the whole thing is done? Usually I think of this as being the point at which we sort of, we go around this loop either across the top or across the bottom many times. Eventually we end up back here and something weird happens to signify that we're done. Can anyone say what will happen when we're actually done at this point? What do you see on the tape? We have to imagine the string at this point everything has been turned into a marked letter. What's going to happen? Yeah? Yeah, we will, because the entire string has been marked, we're going to do this little loop a bunch of times. Actually, all the way, this little loop will carry us all the way through the entire string, all the way to the end, and we'll see a blank. So if you're in this state and you see a blank, that means you're done and the string should be accepted. So here, there's no real funny business here. We just immediately accept from that state if we see a blank. Because the only way that's going to happen is if this little loop right there ran us through the whole string. All right. This was our little warm-up. Any questions about that? Looks kind of complicated, I suppose. All right, I have one for you all to try. And as promised, I brought all my markers here. I thought it might be fun for us to sort of stand up and do some on these boards. So we have, I guess, maybe there are 9 people here, so maybe you could do groups of 3. Would you mind if I just say, like, you 3? And how about the 3 of you in the front here, and the 3 of you in the back? Can be another group. And we have 3 of these boards here. This is going to be so awesome. Let's bring this over here. Oh, there's no wheel over there. Be careful. So here's what I want for you all to try. I'll leave this one on the screen, although what I'm asking you to do is not exactly a variation on that, but it still has this kind of branching paths. This is XCX, where X is in AB star. It's like Charlie. Isn't that somebody? Is it XCX Charlie or Charlie XCX? Does that mean something? I don't know. She's somebody. What does the XCX mean? Nobody knows. All right. It must mean something to somebody. Try that out. See what you think. All right? Yeah, I'll let you think about it. It does have this kind of 2 branching paths scenario. So each, you guys can come over here. You guys can fight about which one you want. And I got all these markers. Go for it. Maybe I'll look up what XCX Charlie means.
gonna have to be 2 branches here. Find an A, find a B.
Do I need A bar, B bar?
I think A bar, B bar comes after C.
Yeah.
So you need to look this through these marks.
Yeah, you have to, you can't just mark an A, mark an A.
Yeah.
You have to mark an A, go until you find a C, and then go to A.
Gotta go through B's, C's, and potential A's.
And then.
So I guess we should probably draw the.
You can start with the 2 branching paths, depending on if you start with A or B.
Transition. Like that.
Ooh,
It could be, yeah.
But-
Yeah.
This is good so
So
far.
we have an A.
You guys feel good about it?
Could you just put like a C bar or C?
Yeah.
And 6
And then go through.
This thing's not very accurate.
I don't know, we have to go back through, right? That's just a very top.
Can you give one of them a turn to right? I don't need to police your boot so much. I have one other comment,
Yeah, I
something
think that's it.
about
Is there shouldn't be any marked letters?
here you go across the C either way, and so to the right here. Then you go back all the way back to the end, at some point you're gonna have to.
We're also gonna have to go
again,
through
which
A,
is not.
A bars and B bars together, so,
Yeah.
and also regular B's.
Right, that's when you're going back to the left, you would get stuck.
Yes, so C would be.
Yeah.
Yeah, that's like what it would be. And then we'll probably want another that would then go through marked letters. Like,
We have our A today.
let me write it up there.
I think it's also going to start the L. I think this is the same.
That's the same.
Yeah, we go through,
Like,
we go
if
through
we
C,
mark
B's,
this, if you mark
and we
this
go
off,
until we get back to a bar.
I'll go through.
So, yeah.
After you go through this,
A.
I'll go through any marked letters, and then as soon as you see unmarked letters, mark it. Cause then you're marking B, any marked letters.
All your cards again.
They mark it up.
Yeah.
So that's
Yeah.
go through marked letters.
Except you state.
I think that we actually have to do
Yeah.
that.
So this one is from A back to, we
No,
can mark the
because
A.
Yeah.
I think like,
So you
because we
don't
need to
want
go
that.
through a bar, we like, we
Yeah.
find, need
Oh,
to
that's
find
true.
a
They would
bar.
have, like,
So we do need this C in the
circle.
middle.
So yeah, I think it would be
So
better.
then we're like,
Letter C.
Yeah, I think you're right.
We might need, it might be like 2
And then
circles.
in case accident thing, we can just do CCR there too.
Okay.
And then this will go, this will mark.
Yeah.
Yeah, I think so.
Yeah. And we're gonna go all the way to the left.
Oh, yeah, this should be.
Yeah. So we need to do.
Yeah. So this would list that.
I think kind of like that one, yeah. Do we want it to look through everything or just all of the unmarked? Define the first
I think
bar.
this is great overall.
Like-
One
I think
thing
it'd
that
be harder to
concerns
just
me
stop it.
is if there was a string
Actually.
that had
If we like,
extra stuff on the end of it.
No, you're right,
Say
it would,
like-
it wouldn't be, yeah.
Take these.
Well, actually, no, because if you're all the way.
Something like this.
No, because you'd be here.
Well,
Seems
at
to
that
me,
point, like,
you would like mark this, go here, mark
We'd have
this,
to go
come
through
back, mark
C,
this.
you have to go through everything.
So you can't go to the first
back
one,
here.
because then you might be missing out on.
no, but if
You
you
would
go
be
all the way
looking,
back
your head would
to the
point at
first
the C.
bar.
And
then
then
move.
point at
I think that makes
the
sense.
C, even though there's extra stuff there. So
So
I think
you
you
go through,
just
but then you have to
down
do
here,
these
you
marks.
do some more stuff that makes the head just go
Like you
all the way to
have
the
to write
right
these
and make
marks,
sure
and
everything's
then
right.
it's unmarked.
And then let's see.
So you might, it might be
Yeah.
pretty
So
slow.
you just need to stay the loop.
And then we'll have probably a loop here.
Yeah, so that should not be accepted anymore.
Yeah.
Yeah. Otherwise, excellent.
Yeah.
That's pretty good. I think it needs to be CCR.
Oh, yeah. No more blank, right?
Yeah.
No more blank,
Yeah.
just CCR?
Yeah. We'll do the same thing as here. No,
Yeah.
Yeah.
I mean, I feel like
So I think it should be A bar, A bar R, B bar, B bar R, and then
We like right there, but you're right.
You need some loops on
Yeah.
that one.
I mean,
I think that that's like everything.
yeah, that's just everything. Yeah.
There you go. That should be right. Yeah, like the world is.
Oh, yeah. I think it's sewer system. That's sewer
Yeah.
system.
The reason I
Is there something different, like if it's
Uh-huh.
not, is it
it's just
unmarked?
because
Oh,
if you
okay.
do
It's like case.
Well, it's
then it's
okay.
up there.
Oh, yeah.
And now,
Yeah.
and then, yeah, we get a blank.
Yeah, that's great.
And then we
I
select
think
that.
yours,
Yeah, that makes
Yeah, I think
is,
it's good. Machines
I
are
think
really
theirs is
good.
a little simpler, and I think theirs is still correct. This state in the middle.
I think that should be good.
So you have it going back a little bit, and then
Same
there's
way.
the C.
Cause if
and
you're
two
gonna go
going
through
back.
like,
I think you can just
Do we need to go through?
put C
I
over
think
there.
there's
and
a
then
C
go
there.
and then it comes
yeah,
back.
fish have a
I
C.
like him so
about
much, but he's.
it.
Yeah.
Because
Going for
You guys have been.
Cause if everything is
Yeah.
marked here, then everything should be marked here.
Yeah, I think this makes it so that as you move to the left, make sure that there's only one C. Which is necessary, but you have already made sure of that with these, and so it's,
She's teaching the other linear algebra right now. I was in that class
you
originally,
can get away with
and
not,
there were 6 people in
that's
it,
what you got.
and there was like me and like 5 guys, and they all like.
Oh, well, I think the reason why was because we have to find this, so we were like, let's get through all of our finished ones and then like segment it. Right, I guess like they did it
Yeah, but I
until
declared it late.
Yeah, so they go all the way to the
Catch up.
left, and then there's a tier on theirs which
Yeah.
pushes you past the marked ones.
What's your major?
Math.
Yeah.
after that.
I didn't get into linear.
That's right, this will do fewer movements
I'm
of
a
the head,
sophomore.
right, yeah.
So I'm
Yeah, it's a-
only gonna
it's
take.
a
this
trade-off,
semester if
yeah.
I get in.
Yeah, like this example that I did is fairly
I feel like
inefficient
you
because it
will
goes
also
all the way back to the
register
beginning every time, even though it's not necessary.
You probably
Yeah.
should.
Yeah,
Yeah,
I think
great.
there's like 12 spots left right now. Like, it's not gonna fill out. Yeah.
All right, I think everybody came up with something great. I'm gonna write it, on the screen just so that I have it in the notes, but I hope that everybody felt good about those. These guys know what's up. There's just a little thing at the end that you need to fill in, but I know they were already talking about it before. All right, you can sit down again if you like. I don't know what else to do with. I think it is interesting to talk about. It seems like the two ones on the far sides have the same basic idea, and there's a slightly different variation here. I think they're all correct, and I don't know the way that I wrote it in my notes is this way with that sort of state in the middle. But we can talk. I said I wanted to write this down for the sake of having it in my notes here. It's like this, right? Now I'll draw it like this one over here, and then we can talk about that one also, what it looks like. So the idea is you mark off the first A here, and then we need to move to the right through unmarked letters. So here I'll say AAR, BBR. Eventually we make it to the C, and I put the CCR there. The C is kind of like playing a special role in the middle. And then we move perhaps past some marked letters, A bar, R, B bar, B bar, R. Eventually finding an unmarked A, which we mark This is because, remember, the language was XCX. By the way, a cursory read of the Wikipedia article does not tell me what the XCX means. Maybe I had to scroll further, but I felt badly reading about this young lady during class. I don't typically read about XCX. Charlie XCX. I'm now distracted. Oh yeah, this AAR, I meant to say L, because having marked off that one, now we can begin moving back to the left, although you could probably say R in that position and it wouldn't matter much. And then right here, so here's the difference between this one on the front board and the ones on the sides. So like this one on the side, for instance, this one, it just says go all the way back to the left, all the way back to the beginning of the string. And that's totally fine. This one over here, and this is the way that I'm going to write it, although both are fine, I'm going to say CCL. So here I said A bar, L, B bar, L. And I think that's all I'm going to say on this one. So this one has many more things on that state, but I'll say why. Then the CCL, then we continue going left through AAL and BBL. Finally arriving at A bar R or B bar R. So the difference here is this one moves all the way back to the beginning of the string. It sees a blank on the left end and then moves back to the right by one position and ends up here pointed at the very first letter in the string, which may have already been marked. And so there's this little looped edge right here moving past some initial marked letters at the very beginning. Whereas this one here actually does not go all the way back to the beginning. First of all, it only moves past the marked things, and then it sees the C in the middle, continues moving to the left, moves past some unmarked letters on the left side of the C, but as soon as you get to one of the marked letters, stops right there. So this one actually does not go all the way to the beginning of the string. It only goes back to, it only sort of goes back as far as it needs to go. It doesn't go all the way to the very beginning. So in that sense, these fine people here said, oh, well, this is more efficient. It does fewer steps, and that's true. The head will not move all the way back to the beginning. Although, so it is more time efficient. You might say it is less space efficient or something because, I mean, the diagram is more complicated, right? It has an extra state here. But anyway, so the other branch that goes across the bottom is just the same, but with B's and A's interchanged. So this will say BB bar R, and then a loop here, BBR, AAR, and then the CCR, and then this one will say B bar L. All right, excellent. And then how do we know that we are done? We are done, you can see in these two examples, when you're in this state and you see a C, that means to the left of the C, everything has been marked off. And so the first sort of unmarked letter that you see is the C. That means you have marked everything on the left side of the C. You do need to do one last trip down the end of the string to make sure everything on the right side of the C has been marked. And so from here, we should say CCR, and then I'm going to go through the whole string and make sure that everything to the right of the C has been marked. So I put a little one of these, A bar R, B bar R, and then finally blank R, like that. That's what they said, and I agree, and that's what they said too. All right, I hope that that came together for you all. Any questions about this one? Everybody seemed to be doing great, so I'm pleased. All right, let's talk about something a little different. So this is the end. We've had maybe like 4 different class meetings of just like more and more examples of Turing machines. I'm satisfied at this point with that. Of course, there are even more complicated things that you can do with Turing machines. Far more complicated, actually, but we will get to some other more complicated things eventually. I want to talk about a slightly different viewpoint on Turing machines. I decided to stand on the other side of the room today. I want to talk about what we call Turing computable functions. All right. So Turing machines, you know, as we've been discussing them so far, are just like a thing which either accepts or rejects a string, you know, kind of like DFAs or stack machines or whatever else. Although we can, because the Turing machine has a tape and the machine itself can change the values on the tape, we can view a Turing machine as a much more sort of recognizable, conventional kind of computing machine. I'll say we can view a Turing machine as a computing machine which takes some input on the tape, and rather than accepting or rejecting, since there's a tape, we can think of the Turing machine as changing the input around and then stopping with some sort of output. So we can think of a Turing machine as a computing machine which takes input and gives an answer, like a specific answer, on the tape. All right? This is a different way of thinking about, so in this context, we're actually not going to talk about accepting or rejecting. We're going to talk about you stick a string on the tape and then run the machine, and then the machine will stop with some other string on the tape, and that will be the answer. All right? So this is a viewing the Turing machine as a computer which takes a certain input and then gives you back a certain output. All right? So, for example, this is a very simple example. I'll call this Turing machine M. Let's say A, L, BBL, and then blank A, R. And that's it. All right? So this Turing machine has no accepting state. That's because I am not thinking of this as a thing which accepts or rejects a string. I'm thinking of this as a computer which begins with some string on the tape, and then it does some stuff, and then it ends with a different string on the tape. All right? So let's try and decide what exactly does this do. So if we start, let's say, something like AAB on the tape. You know, if I were to sort of draw a picture of the tape, it would look like AAB, and then followed, of course, there's always like infinite blanks on either side. Blank here, etc., right? If we start with AAB on the tape like that, and you know, the head always starts off pointing at the first letter in the string, what happens? That's my question. Well, you can see what happens. First of all, in the starting state here, it says AAL. That means I read this A, leave it like that, and move one position to the left. And then what happens next? It says blank AR. The output, this becomes, after you do all these steps, this becomes, the head will have moved one spot to the left. So I still have a blank here, but this becomes a A. And then A, B, blank, blank, etc. All right? That's what happens when this Turing machine runs. It's pointed at this A, and I suppose when we finish, the head will be in this position. Maybe it'll move to the right after. I don't really care where the head is at the end, but I think it'll technically be in this position, right? You see this A, you move to the left by one position, and then you write an A there, and then move back to the right. All right? So if we start with AAB on the tape, the result is now the tape says AAAB, right? So here we can think of this as a function. We think of this Turing machine as a function where apparently this function looks like this, f of A, what was it, AAB? That's what we started with, and what was the answer? The answer was AAAB, right? I'm thinking of this machine as a function. So when I say this, what I mean is if I start the Turing machine with AAB on the tape, so this, what that means is if we start with AAB on the tape, then the Turing machine does its thing. It does a bunch of steps. And I will say the Turing machine halts. That is, at some point it just stops with AAB on the tape. All right. That was just one particular example. If I start with AAB, the answer will be AAAB. Can we say in general, generally, if we start with some string x, it ends with, in this example, I think no matter what we start with, what the machine says is just go left once and then write A. I think that means if we start with the string x, it ends with the string AX, right? No matter what we start with on the tape, it's going to just move, the head will move one position to the left and then write an A in that, what used to be a blank, all right? So if we start with x, it ends with AX. And we say, in this example, we say M computes F, all right? M is the name of my specific Turing machine here, and the computation, I meant to say, this particular function, f of x equals ax. That's an equation for the function. F of x equals ax. M computes that function, all right? This function, usually we often, write the domain and the codomain, this is often helpful, the domain and codomain of f. I say f goes from, this is like you wrote in your discrete math class. F is a function going from AB star to AB star. That is to say, this is the domain of the function here. What you plug into f is any string of a's and b's. And this is the codomain. That is what kinds of things come out of this function. They are, again, strings of a's and b's. But the definition, the formula is this, f of x equals ax. All right? This is viewing the Turing machine as a function that takes some input and then gives you some answer. All right? The big question that we have now, this is sort of a new type of question that we can ask here, or here, let me just say a definition here. Some function f is called Turing computable if, what does it mean if I'm imagining a function and I say that function is or is not Turing computable? It is called Turing computable if there is some Turing machine that can actually do that function. So some function f is called Turing computable if there is a Turing machine which computes f. All right? In that case, the function is called Turing computable. So the example that I just discussed before was f of x equals ax. This is Turing computable. And the big question that we're going to be asking for the next couple times is just like, what kinds of functions are Turing computable? This is a very simple function. All it does is stick an A at the beginning of a string. Yeah?
Since a Turing machine is just like a basic form of a computer, like, wouldn't a Turing machine be able to compute anything that a computer is able to compute?
Yes. Yeah. So my question, so it is true that a real-life computer is essentially a sort of big and fast Turing machine, right? So my question, which functions can be calculated by a Turing machine, is actually equivalent to asking which mathematical functions is it possible for a real-life computer to compute. And that is also an interesting question. I think if you just ask a random person on the street, hey, what kinds of mathematical functions can a computer calculate? I think most people's answers would be like anything. Isn't that like a mathematical function? A computer should always, in theory, be able to calculate it. Such a person is wrong, though. Actually, there are certain functions, mathematical functions, which cannot be calculated by any Turing machine. So not all functions are Turing computable. And what that means is, in terms of real life, it means that there are actually certain functions that no computer can calculate. But we're going to get there eventually. But anyway, this is the idea. Can we do? I want to do one more very simple example, and then see if you guys can do some also very simple examples, and then we'll talk about some less simple examples. But how about your job? Or well, I'll do one first. How about let's try f of x equals xb. All right. So the question, as you might see it on your homework or on a test or something like that, I could say something like, is this function Turing computable? Is it Turing computable? The answer is yes. The way to demonstrate that is, here is a Turing machine which computes that function. All right. This one is actually, I suppose, slightly more complicated than the previous one. The other one was AX, and to put an A at the beginning, all you have to do is move left once and then put an A. Anyone want to just suggest in words how my strategy should be? Here I need to start with a string and put a B on the end. Yeah?
Move right until blanks, and then change the blank into a B.
Yeah, move all the way to the right until you see a blank. So the way we do that, we already know how to do that. That would be something like this, AAR, BBR. Until you see a blank. And then he said, change the blank into a little b, right? Little b, is that a wrapper? It should be. How would I do that?
BBR.
BB, can you be more specific?
Blank BR.
Yeah, blank, little b, r. I think that'll do it. All right. Again, when you're using Turing machines in this context, we don't use accepting states. Just the machine will just stop when it gets here because there's no outgoing arrows. And so, yeah.
Like, would you be able to use accepting states here? Like, what if you combine them? What does that do?
I would say, if you put in if you made this an accepting state, I am not entirely sure what that is supposed to mean, but I wouldn't say it's wrong. But the Turing machines, which we have been talking about before, their whole purpose is to either accept or reject a string. And in that sense, you need to have some indication on the diagram of what is accepting versus what is not accepting. But here, the machine is not meant for that purpose, and the diagram is not supposed to accept or anything. The whole point is you start with something on the tape, and you finish with something else on the tape. It's kind of like everything is accepted. Nothing is rejected, really. It's just whatever you finish with. All right, great. I got two simple ones for you all to try. How about f of x equals axb? This just sort of combines the previous two. And here's another one. F of x equals the empty string. Think about that. So these are two separate examples, all right? See if you can. In each case, make a Turing machine which computes that function. Because for instance, if I start with just A on the table, then this doesn't mean yeah, this is fine. State wonder. Now right here, this is a computer. Yes. I like this. Because you need to, whatever the string begins with, in order to create this A, you have to move to the left one position and make the new A. Like this doesn't actually make a new A, it just looks at A and then moves to the right. Yes, and what's that? Is that on here? Yeah, and you have to move to the left. Because you only can be looking at this one unless you go to the left first. So there should be another state first, which points to the left. And then do that. Looks like people are doing just fine here. All right, can we chat about them? People seem to be doing fine. This one, AXB, this is what I did for that one. So in order to put the A at the beginning, you imagine the tape begins with X on it. In order to write the A at the beginning, you have to move one spot to the left, which I did with this. Either it's an A to begin with or a B to begin with. I moved to the left by one, and then that blank on the left, I turn into an A. So this creates the first A on the left side, and then we go all the way to the end. That's this loop, and then change the blank at the end to a B. And then that L could have been an R, it doesn't matter, going here, right? I saw some people insisted on making this an accepting state. I mean, you do you, but you don't typically write accepting or not accepting states. Well, we write everything as a not accepting state. All right, and what about f of x equals epsilon? I saw more than one person just sort of did this. Although this will sort of, if you start with nothing, this sort of keeps it as a nothing. But the idea of this machine is no matter what you start with, you need to turn it into nothing. Yeah.
Just you do a single state, and then the loop into the state is A blank R, B blank R.
A blank R. Yeah, I like this. B blank R. This runs down the entire string and just deletes every letter. And eventually, this will run to the end and then get stuck when you see a blank at the end of the string. Yeah, great. So this is the f of x equals epsilon function. All right. We got a couple more minutes. Let's just try one more example that's a little more interesting. The domain of these functions is often not all strings. Like, for example, here is a function. Let's make a Turing machine for this function. F of b to the n, a b to the n equals b to the n, a squared b to the n. All right? So this is a function which you don't just plug any old string in it. You can only plug strings of this format into it. That's what I mean. The domain is not all strings here. So you are only plugging in strings which have this particular format, some amount of b's, then one a in the middle, and then some other amount of b's. And the result I want to be this, all right? So if I were to explain this in words, it's just I have one A in the middle to start with. The answer, I want to be the same thing but with two A's in the middle instead of just one, all right? And the simple method would be you find that A in the middle and then you just kind of like bump everybody down by one position and put a new A. Although perhaps you remember, there is no thing in a Turing machine diagram that says bump everybody down by one position. You have to be a little more nuts and bolts about this. You got a strategy?
Yeah, so you find the A, and then to the right of the A is a B, so you go turn that B into an A, and then you go all the way to a blank and turn that blank into a B.
Yeah, right. So the strategy is you find this A first of all, and then the next B, you make it an A, and then you go all the way to the end and you add an extra B at the end to compensate for the one that you erased in the middle. Yeah, this is a good strategy. So it would look something like, first of all, you move through all the B's at the beginning. So I'm going to say BBR. And then eventually you get to the A in the middle. That A should stay like it is. So I'm going to go AAR. That's the A that already existed. The next letter is a B, but I want to make it into an A. So here I'm going to say B, A, R. That is putting a second A right here. Now I just destroyed one of the B's. In order to keep the same amount of B's at the end, I'm going to run to the very end of the string and put another B there. So here I will say BBR. Running through all the rest of the B's on the tape. Eventually we get to a blank at the end, and I make that a B, like so. All right? This assumes that n is not 0. Right? Because in order for you to actually make it through here, you have to actually see at least one B in there. All right? If I wanted to make it so that it works even if n is 0, I think you could just do something like, so maybe I'll add it in. If n is 0, you want like a special case here. You would see a blank, and I would turn that also into an A. So if there were no B's at all, you would just see the A immediately, and then you would see nothing. You should make another A to make it so that there's now two A's when there used to be one. All right. I think that'll do it. So next time we'll do some more complicated and more interesting examples of this type. All right. Let me know if you want to talk about the homework. I would be happy to